Hello, everybody. Today, I would like to give you a lesson on the topic determining the area of a triangle. Don't forget to subscribe to my channel and like it. I would be very grateful. Now, let's go. Imagine one day you went to the Flatiron Building just to admire the view. Suddenly, the owner of the building approached you and politely asked, "Please calculate the area of this building for me." And at first, you were confused and didn't know where to start, and you needed to take a floor plan, determine the shape, and calculate the area using the well-known formula, which you will learn about today. That's why you need knowledge about recognizing the area of a triangle, and not only. So be attentive in this lesson. It will be quite interesting and unusual for you. First, let's find out the formula for calculating the area of a triangle using the height. The formula for finding the area of a triangle by height is half the product of the length of the side, base, times the length of the height drawn to that side. The formula looks like this. S equals 1/2 times A times H, or S equals A times H divided by 2, where S is the area of the triangle, A is the length of the base, and H is the length of the height drawn to that base. And we have the formula for calculating the area of a triangle using the sine. The area of a triangle is equal to half the product of its sides and the sine of the angle between them. First, let me prove to you why the area of a triangle is half the product of its side times the height drawn to that side. So we take the rectangle AEDC and we take the triangle ABC. Let EB equal BD, BH equals the height, AC equals A, and let BH be perpendicular to AC. So the area of the triangle AEB will be equal to the area of the triangle ABH. The area of the triangle BCH will be equal to the area of the triangle BDC.
Hence, the area of the triangle ABC is equal to half the area of the rectangle AEDC. If AE equals BH equals H, the area of the rectangle AEDC equals H times A. That's why the area of the triangle ABC equals 1/2 times A times H.
I can also prove to you that we can find the area of a triangle using two adjacent sides and the sine of the angle between them. So we know from the previous slide that we can find the area of a triangle as half the product of the height times the side to which this height is drawn. So the area of triangle ABC is 1/2 times BD times AC. Instead of AC, I will substitute B. Let's take a right-angled triangle BDC, and we will have that the sine of the angle gamma will be equal to BD divided by A. And now from here, BD will be equal to A times sine gamma. And instead of BD, I will substitute A times sine gamma, and we will have the formula that we wanted to prove. We have another formula for calculating the area of a right triangle. The area of a right triangle is equal to half the product of its legs. Take a look at the formula for finding the area of an equilateral triangle is S equals A squared times the square root of 3 divided by 4. In this formula, S is the area of the triangle and A is the length of the side of the equilateral triangle. Let's prove it. Well, we take a rectangle where two sides are A and B. We know that the area of a rectangle is equal to the product of two adjacent sides. Now, if we take away 1/2 of this rectangle and we get a right triangle. And therefore, the area of a right-angled triangle is equal to half the product of its legs, which is half the area of the rectangle. Well, now let's prove the formula for finding the area of an equilateral triangle. We have an equilateral triangle ABC. Let's say that one of its sides is A. The angle C is gamma and BD is perpendicular to AC. So let's take the triangle BDC. We know that it will be right-angled. So the sine gamma will be equal to BD divided by A. Hence, BD is equal to the product of the side of the triangle by the sine gamma. The sine is 60 degrees. We know that the sine of 60 degrees is the square root of 3 divided by 2. And why did I take the sine of 60 degrees? Because all the angles in an equilateral triangle are equal, and all are equal to 60 degrees. Square root of 3 divided by 2, I will substitute into this formula, and BD will be equal to A square root of 3 divided by 2. Now the area of the triangle ABC, we know that it will be equal to half the product of the height by the side to which it is drawn. So instead of AC, I will substitute A. Instead of the height of BD, I will substitute A square root of 3 divided by 2, and we will have the formula that we wanted to prove. We move to Heron's formula. The area of a triangle with sides ABC can be calculated by the formula. S equals the square root of P minus A times P minus B times P minus C, where P is its semiperimeter. Well, these formulas for calculating the areas of triangles inscribed and circumscribed around a circle may come in handy someday. Remember, a circle can always be circumscribed around any triangle, and a circle can always be inscribed in any triangle. Also, remember that the center of the inscribed circle lies at the intersection of the angle bisectors, and the center of the circumscribed circle lies at the intersection of the perpendicular bisectors of the sides. Let's prove each formula step by step and separately, but let's start with Heron's formula. We don't need a drawing to prove this formula. Well, we know that we can find the area of any triangle by multiplying the adjacent sides by the sine of the angle between them. So let's square two sides of this formula, and then we'll remember the law of cosines, and remember how we can express the cosine of an angle from this formula. And then we'll remember the basic trigonometric identity, which says that sine squared gamma plus cosine squared gamma is equal to 1. And from this formula, we can express sine squared gamma. It's equal to 1 minus cosine squared gamma. We will now use the formula, one of the formulas of abbreviated multiplication, the difference of squares of two expressions. Then in this formula, instead of the sine squared gamma, we will substitute what we have just found. And then, instead of the cosine gamma, we will substitute what we can express from the theorem of cosines. Now we can take out after calculating 1/16 in brackets. In brackets, we will get the corresponding values. Then we can decompose this product of expressions into 4 factors, and applying to the second and third products also the formulas of the difference of squares of two expressions, we will respectively get the following factors. We subtract 2a, 2b, and 2c from the first, from the second, and from the third factor. For what? You will understand now, so that we can then derive the formula. And we know that a plus b plus c will be equal to 2 semiperimeters, because in geometry, the semiperimeter of a polygon is half its perimeter. The 2's are cancelled out, and notice that we got this long expression when we found s squared. In order to derive Heron's formula, we have to take this expression as the root. That's it. Let's move to another formula. And so we have a triangle ABC. AB equals A, BC equals C, AC equals B, AO equals OC equals R. Angle C is equal to alpha. And note that this triangle is inscribed in a circle, and the hypotenuse of this triangle lies on the diameter of the circle. So let's remember that the sine of alpha in this case will be equal to the ratio of the opposite leg to the hypotenuse. So the sine of alpha will be equal to A divided by 2r, because the hypotenuse is the diameter. The diameter is 2r. So remember the same form for finding the area of a triangle, and instead of sine of alpha, I will substitute what I just expressed, and I will get the formula for finding the area of a triangle if we have the base of its side and the radius of the circle circumscribed around this triangle. Note that we write the radii r of the circumscribed around polygons with a capital letter, and if this circle is inscribed in a polygon, then we write it with a lowercase letter. We can also prove why the area of a triangle circumscribed around a circle will be equal to the product of the semiperimeter of this triangle and the radius of the circle. So I will explain to you in advance the course of this proof. We must divide the triangle ABC into 3 triangles and find the area of each triangle, and then add their areas, and we will get another formula for finding the area of a triangle. So let's first take the triangle AOB. We will find in it an area that will be equal to 1/2 RA. Then I will take the triangle AOC. We will find in it an area that will be equal to RB. Now in the triangle BOC, we will also find an area that is equal to RC. Now we add all these areas, we will take out the brackets R, and we know that if we add all the sides of the triangle and divide them by 2, then this will be the semiperimeter. So we got the formula for finding the area of a triangle when we are given its semiperimeter and the radius of the circle inscribed in this triangle. We finally move to our problems. Determine the area of the triangle using the given data. Look at what we are given. A triangle, its height is drawn in blue. This is marked. It is lowered onto this green side, which is also given to us. Therefore, since there is a height, it is better to use this formula now. A is the base, I marked it in green, and the height in blue. We substitute, calculate everything, and we have 6. Next, please look, this is a right triangle. I highlighted one leg in green and the other leg in blue. If we know the formula for calculating the area of a right-angled triangle, then we can substitute these values, and we get that the area will be equal to S equals 1/2 times 2, and by 7 is equal to 7. So the answer is 7. Let's look at another problem. The plot is 2 sides and the angle between them. If such a picture, then it is better to use this formula. This is when we have 2 sides and the angle between them. This is the area of such a triangle, one side B by C by sine alpha. Substitute. We have B, the green side, 10, blue, 11. Just pay attention. You do not have sine 150 in your reference materials, but you can use this formula, and you have such a formula. Look at your reference materials. Here, where is trigonometry? Sine of 180 degrees minus alpha. I presented it in this form in order to use this formula. 180 minus alpha is simply sine alpha. That's what I wanted to explain to you where I got it. And sine 30 already has the tabular value of 0.5. And when we substitute this number 0.5 here, well, that's it. There is already an area, 27.5. And the fourth problem, such a plot. What to do here? When you have all the sides given, then it is easier, quickly, Heron's formula. But first you need to find the semiperimeter. Look, I will specially highlight the sides in different colors. Green, blue, brown. We substitute them. 13, 14, 15. Divide by 2, this is 21. and we substitute everything into this formula. And these sides, the green side, 13, is substituted here. The blue side, 14, is substituted here. And the brown side is substituted here. And here is how it looks, of course, after the substitution. An unpleasant expression, I agree, but if you start calculating, you can do such miracles. What does miracles mean? The number 21, it can be represented as 7 multiplied by 3. The number 8 can be represented as 2 multiplied by 4. Why do I factor it like that? Because this 7 and this 7, that's 7 squares. Then 3 multiplied by 2, that's 6. And here's 6. 6 by 6, that's 6 squares. And there's still 4 left. That's what root I'll have to find. The square root of 7 is 7. The square root of 6 is 6. The square root of 4 is 2. That's the answer, 84. So if you understood everything today, and it will help you a lot in the next lessons, I would give you Kia Sportage as a gift. If you are worried or excited because you didn't understand something, no problem. Watch this video again slowly. Never give up, and I wish you to understand it as soon as possible. Bye.